Hello students, welcome to this lecture number 7 on thermodynamics. In the previous lecture, we have discussed about different types of enthalpies, like enthalpy of reaction, enthalpy of formation, enthalpy of utilization, and enthalpy of combustions. All are very much important enthalpies. To understand this enthalpy, we have also discussed some numericals in our previous lecture, that is lecture number 6. If you have not watched this lecture, you will see, and it must be beneficial to you to understand the concept of types of enthalpies. In this lecture, we are going to discuss different other enthalpies. So today's heading of this lecture will be type of enthalpies part 2. So you can write that today's heading of lecture is type of enthalpies. Type of enthalpies, that is part 2. In this lecture we will be going to discuss different type of enthalpies. That is very much helpful to your syllabus point of view. First, we will discuss the enthalpy of atomization. Enthalpy of atomization. And this is being represented by delta H A, and we will discuss the standard enthalpy of atomization. Then we will discuss the bond enthalpies. Bond enthalpy. Bond enthalpy is being represented by bond. You have to write bond. This is bond enthalpy. Number 3 that we are going to discuss, the enthalpy of salvation. So in this lecture we are going to discuss first the enthalpy of atomization, then we will discuss bond enthalpy, then we will discuss the enthalpy of solution and lattice enthalpy. All are very much important in your syllabus point of view. So first let us understand what we mean by the enthalpy of atomization. Enthalpy of atomization is basically the energy required to break 1 mole of bonds to produce the atoms in the gaseous state. So let us take the example of the atomization of hydrogen gas. This is hydrogen gas, and it is atomized and produce 2 hydrogen atoms. In this process, the enthalpy change in this process, when 1 mole of bonds of hydrogen bond has been break. This has been break, and it is going to produce the hydrogen atoms in the gaseous state. In this process, the enthalpy change that we are taking in the standard enthalpy change of atomization, in this process it will take around 435.5 kilojoule per mole of energy to break this bond, and this is called the enthalpy of atomization of hydrogen molecules. When we break the 1 mole of hydrogen bond to produce the hydrogen atom in the gaseous state. Another reaction you can take to understand the enthalpy of atomization, that is for methane gas, and it will be atomized and it will going to create a product, that is carbon and hydrogen in the gaseous state. In this case, the enthalpy of atomization is found to be plus 1565 kilojoule per mole. So we understand what is enthalpy of atomization. This is basically the enthalpy change accompanied when the atomization process is being followed. Atomization process means when molecules has been transformed into its atoms. In this case, hydrogen molecules, the hydrogen in that atoms has been formed in the individual atoms in the gaseous state. Here also you can say methane gas has been converted into the atomic state, that is its constituent, that is the carbon and hydrogen. And another example that is taking that is the carbon sodium. Sodium in the solid state, when it is being converted in the gaseous atom state, at that time this is also a enthalpy of atomization, and in this case the energy will require, that is 108 kilojoule per mole. It is also called the enthalpy of sublimation. Enthalpy of sublimation or enthalpy of atomization for this. So now we understand what we mean by the enthalpy of atomization. Enthalpy of atomization is basically, it is the energy required, or we can say the change of enthalpy accompanied when there is a reaction of atomization from the hydrogen gas to the hydrogen atom. Okay, now we go to the another next important enthalpy, that is the bond enthalpy. So next enthalpy we are going to discuss, that is enthalpy, bond enthalpy. That is bond enthalpy. That is very important enthalpy. We must understand totally. Bond enthalpy is represented by delta H bond. Bond enthalpy, we can understand a very important thing, that it is correlated. You can relate this bond enthalpy with the heat of the reaction. Because in the reaction you will find that there is the breaking of the bonds, means breaking of the old bonds, and creation of the new bonds normally being there. So when we break the bond, we have to give some energy to the system, and when there is a formation of the bond, there will be the energy release. So we can able to correlate this during the enthalpy change of the reactions, and we can correlate with this bond enthalpy. In thermodynamics, when we correlate the bond enthalpy with the heat of the reaction, there is two terms normally we use for this bond enthalpy. That is, number one, bond dissociation enthalpy. Bond dissociation enthalpy. Very important term that we come across. Bond dissociation enthalpy. Number two, that is mean bond enthalpy. Mean bond enthalpy. Both these two terms is basically being for the different types of molecules. When there is the diatomic molecules, diatomic molecules means that is hydrogen molecules, oxygen molecules, nitrogen molecules, chlorine molecules. These are diatomic molecules. For these diatomic molecules, what you find, that is the when we break the bond, 1 mole of bond, we will call the enthalpy associated with this reaction. That is, as per example, we take the example of this chlorine gas. We break this chlorine gas, it will produce, chlorine gas means the atom bond of the chlorine gas, chlorine molecules, that will going to create a atom. In this case, you will find the enthalpy of atomization is coming around 242 kilojoule per mole, and this is called the bond dissociation enthalpy. This will write the dissociation enthalpy. Dissociation, bond dissociation enthalpy is this. So we can see, previously we discussed the enthalpy of atomization. Now we are discussing the bond dissociation enthalpy. They are basically same for the diatomic molecules. They are normally same. For the hydrogen gas, you can also see this. This is about bond dissociation enthalpy. Bond dissociation enthalpy and the bond enthalpy of atomization. Both these are same thing for the diatomic molecules, that we have to remember. But for the polyatomic molecules, the bond dissociation enthalpy is different for different atoms with different bonds. Polyatomic molecules, as for example, you can see that is methane gas. Methane gas, when atomizes, and it will produce this. In this case, what has been found out, that the bond dissociation enthalpy of here, you can see there is a 4 carbon-hydrogen bond, 4 carbon-hydrogen bond, and all the bond, it has been found, although the bond have the same strength, bond have the same length, still when we are going to break the bond, then the bond dissociation enthalpy will be different for the different bond. That can be easily visualized from here. From the data, you can easily able to visualize a very factual thing, that the bond's enthalpy of every CH bond is different. That you can see, for this bond it is 427 kilojoule per mole. For the second bond, we are the successive breaking of the bonds, that we will see the 439 kilojoule, and the third bond, that is 452, and this. And when we make a summation of this, it will coming around 1665 kilojoule per mole, and that is the enthalpy of atomization. So we will see that every bond having the different energy. When we break this bond, it will require different energies. So at that time, the bond dissociation enthalpy will not going to be practical one. You have to use another term, that is mean bond enthalpy. Mean bond enthalpy you have to see, and that will get the mean bond enthalpy. When we divide it by 4, it will coming around 416 kilojoule per mole. So we can write in this process in CH and H. This is the mean bond enthalpy. So we understand what is bond enthalpy, what is enthalpy of atomizations. Now we will discuss one very important thing. As we have discussed one thing, that when there is a chemical reaction is going on, means there is the breaking of the bond and the formation of the new bond. And in this process, what is going to happen? There is a liberation of the energy, or maybe sometimes the energy will be absorbed. So heat of the reaction, or you can say enthalpy of formation of the reaction, can be easily be found out from this bond enthalpy data. Now how can we make it? Suppose we don't have the enthalpy of formation data of the compounds from which a material has been produced. At that time, this bond enthalpy will be helpful, but this is applicable for the gaseous reaction. So what we will write, that is enthalpy of reaction. Enthalpy of reaction is basically, we can say, summation of the bond enthalpy of reactant, minus bond enthalpy of product. And from this we will able to understand the enthalpy of reaction when we do not have the data of enthalpy of formation, because from the enthalpy of formation you can able to calculate the enthalpy of the reaction. But when you do not have, we can use this, and this is applicable only for the gaseous reactions. So now we will do one numerical, and that will be help you to understand clear the concept more. We have discussed about the bond enthalpies. Now related numericals, this type of numericals will come. You have been given a reaction where the enthalpy change is giving here, this minus 571 kilojoule per mole. In this case, you have been given the bond energy of this. You can see this is the bond energy, bond enthalpy. Bond enthalpy of hydrogen is 435, oxygen is this, and then average bond energy of this OH will be that the option is given. How do you do this? You just use this formula, simple formula, that is we are using this, that is first we have to see the reactant here. 2 into hydrogen bond enthalpy is bond enthalpy of hydrogen, because the two molecules are there, so this is this, plus that oxygen bond energy of oxygen, minus this 2 into this will be not 2. Here you can see that is H2O having a molecule having this structure, right? So there is a 2 bond, so total we have 4 into OH, 4 into bond enthalpy of OH, that we have to discuss. That when I put this value, that's 2 into 435 plus this will be the 98 minus 4 BE, bond energy of A, and this is giving here this. So we will just put it minus, this will be minus 571. So from this, if we calculate, we will get the bond energy of OH, oxygen hydrogen bond, that is coming around 484. This. So this type of numericals will come. Now we are going to discuss a very important Now we are going to discuss a very important enthalpy, that is the enthalpy of solution. Enthalpy of solution. Enthalpy of solution, it is represented as delta H solution, and for the standard this we have to put this symbol. What is enthalpy of solution? Enthalpy of solution is basically the enthalpy change. This is basically the enthalpy change. You can write the enthalpy change when 1 mole of substance, 1 mole of substance dissolved in a specified amount of solvent. Specified amount of solvent. When the solvent is specified amount of solvent. When the solvent we use infinite amount of solvent, then the enthalpy of solution will be at the infinite dilution. At that time, the enthalpy of solution will be different. But we are not discussing that. We are discussing this when we put some substance in a specified amount of solvent. At that time, what is the enthalpy change? So, this enthalpy change, suppose to understand this, we are taking that ABS is a ionic solid. It will dissolve and it will produce ions in the aqueous medium, and it is being like this. But what happens there? It is not so simple that what we have seen. There is a two process involved here. First, the ionic compounds, when it is dissolved, it will leave its ordered position. We will understand in the class 12 that for the solid state, that every ionic solid have a very specific lattice, specific arrangements, ordered arrangement. When it is going to dissolve in this solution, it will leave its ordered state and it will go to the solution, and it is now very much free. But there is another process, that is the solvation of these ions. And when it is in the water, it will be a hydration. So there is two enthalpy being associated with the enthalpy of solution. That is, one is the lattice enthalpy. One is lattice enthalpy. In this lattice enthalpy, what is going to happen? It will first be converted into the gaseous ions. It will convert it into the gaseous ions. And again these gaseous ions will be solvated and it will hydrated into the water, and it will, at that time there is also a enthalpy of another type of enthalpy, that is called enthalpy of hydration. So we can write the enthalpy of solution is basically the lattice enthalpy plus enthalpy of hydration. This is very much important, lattice enthalpy and enthalpy of hydration. If the lattice enthalpy is very high, then the substance will not going to dissolve. It will have a very selective value for those which is going to dissolve in the solution, in the water. If it is high, as for example for the fluorides, it has been number of times you will get some questions like this. Why fluoride is insoluble but chloride is not soluble? That question sometimes asked in your exam, At that time, your answer will be the lattice enthalpy of the fluid is very high. That is why it is not going to be dissolved. So here you can see there's two things going to happen. Enthalpy of for the enthalpy of solution, that is lattice enthalpy and hydration enthalpy. Now we are going to discuss what is lattice enthalpy and how do we calculate it. We are going to discuss the lattice enthalpy. That is a very important enthalpy that you must understand. Lattice enthalpy is a very important enthalpy that we are going to discuss. Lattice, you will write lattice in the delta H, lattice enthalpy. Lattice enthalpy is nothing but, it is a very important thing. When it is also an enthalpy change. When the 1 mole, we can write, this is basically enthalpy change. This is basically enthalpy change when 1 mole of substance, 1 mole of substance, that is basically the ionic compound, we will say ionic compound, dissociate into the gaseous ions that we already discussed. Suppose this is an ionic compound and it has been dissociated into the gaseous cations and gaseous anions. Then we will call this is the lattice enthalpy. This is lattice enthalpy. But lattice enthalpy you could not able to calculate, you can able to measure directly. You have to take the help of the very important cycle. This is called Born-Haber cycle. Born-Haber cycle, what is that? Let us first understand. We will take the one example for this that will be helpful to you to understand. We are taking the example for NaCl. NaCl, it is produced for sodium, solid sodium, and you have to reaction with it with the chlorine that will produce the NaCl. So here enthalpy of formation will be this. But this will not a very easy step. There are several steps involved in this production. First, the sodium salt will be sublimated into the gaseous. At that time, the enthalpy of sublimation will be taken care, and in this case it will going to give the gaseous atoms. First it will have the gaseous atom. Then this gaseous atom will with the help of another enthalpy, that's the enthalpy of ionization, that we will find that Na plus ions. You will get the Na plus ions. Okay. In the here also you can see that is chlorine will dissociate. Enthalpy of dissociation will be there, that we have already discussed. Dissociate and enthalpy of dissociation. It will produce the atoms, chlorine atoms. And this chlorine atom will lose one electron. At that time, the enthalpy of electron gain enthalpy, you will find that it will Cl minus. And these two, with the help of the lattice enthalpy, here the lattice enthalpy, it will produce this solid. So, in this formation, you can understand that lattice enthalpy of formation, that is like this enthalpy of formation of this Na plus sodium and chlorine to the NaCl, it will basically comprise of, that is enthalpy of sublimation.
plus enthalpy of ionization plus enthalpy of dissociation, then enthalpy of electron gain enthalpy, then the lattice enthalpy. Then you will get the lattice enthalpy. So this enthalpy you can able to calculate if you know this enthalpy of formation, if you know this, and if you know this, and if you know this, and if you know this. So enthalpy of formation is normally being found out, that is lattice enthalpy is this found out normally 788 kilojoule per mole. When we take the lattice enthalpy and the solution and the addition enthalpy, it is found the enthalpy of solution. Enthalpy of solution, it is 788 minus 784, that is 4 kilojoule. That is endothermic process. Enthalpy of solution is endothermic process, that you have to absorb this energy. So when we increase the heat, the more amount of NaCl will be dissolved in the water. That is why it is so. Enthalpy of solution is positive. And here addition enthalpy you can see, that is negative. So in this way we can able to calculate the hydration lattice enthalpy. And this type of question will come that you have to calculate this lattice enthalpy, you have been given everything. Then you can able to calculate it. Lattice enthalpy. Okay, that is all for today's lecture. In this lecture we have discussed some important enthalpies. Okay. Hope you enjoyed this video. If you like this video, you can share to your friends. Thank you very much for watching. Thank you.